unit commitment problem since the last class. So we talked about the basics of unit commitment, what's the difference between unit commitment issue and the economic load dispatch problem. And we also talked about some of the features associated with unit commitment problem. And then we started discussing about some examples, small examples, like how to solve the unit commitment issue by taking all the possible combinations among the units. And then we formulated a table, and we showed how to actually solve a unit commitment problem by taking all the possible combinations among the listed units. Then we also saw another example of unit decommitment, where we found that if the load varies, specifically if the load drops, then how we are going to actually decommit the units. And again, if the load increases, how we are going to commit the units. So that means if the load varies throughout a day, which is a practical scenario, then how we are going to cope up with that by starting on and shutting down the units. Okay, so we followed a simple shutdown rule for solving the decommitment example. And then we talked about some constraints associated with unit commitment problem, like the spinning reserve issue. Then we talked about the offline reserve. We talked about some reliability issue, that the spinning reserves or whatever reserves, offline or spinning reserve, they should be distributed throughout the system if it is an interconnected system, as is the case in most practical scenarios. Then we solved an example for the spinning reserve problem. And after that, there were a few more constraints discussed, like the minimum uptime, the minimum downtime, the crew constraints, the thermal, the hot, and some of the definitions for some other keywords associated with the constraints of thermal units were discussed. We also discussed about the hot start and cold start costs, their mathematical expressions, their graphical representation. And finally, we talked about some other constraints like the must run unit. What is a must run unit? What is the fuel constraints, and what is the hydro constraint? So today what we will do, we will actually take different structured ways to solve the unit commitment problem, starting with the priority list scheme. And probably we will start the dynamic programming problem. So as I said in the last class, in this course, we will be actually only going through the first two, that is the priority list scheme and the dynamic programming technique. So these two will be discussed in detail in this course. So let's start with the first one, that is the priority list scheme. So in the priority list scheme, what we have to actually do at first, we have to prepare a priority ordering. Okay, we have to prepare a priority ordering to begin with the solution of the unit commitment problem. So again, a set of data will be given associated with the units. So again, let's say we have 3 thermal units, and it is asked that we should prepare a priority list for shutting down the units. So for each of the units, we have the maximum limit as well as the minimum limits. So you can see in the first column, we have the minimum limits, and the second column, we have the maximum limits. Then you have the heat rate in mega or millions of BTU, that is British thermal unit per hour. So all the heat rate are actually given in quadratic form. So all these are actually nonlinear functions of the individual generations for each of the units. The fuel costs are given in dollars per millions of BTU, and the demand is constant, that is 550 megawatts. So for preparing the priority list among the units, first we will calculate a term or a cost which is known as the full load average production cost. And the formula is actually shown over here. So the full load average production cost is expressed as, or the calculated as, the heat rate and millions of BTU per hour. So that means this one, if we take unit number 1, so we have to take heat rate for this one, and we can see that this is a function of PG1, nonlinear function, of course. So if I want the numerical value for this, then what I have to do, I have to replace this PG1 and PG1 square over here. So because we are talking about the unit number 1, so you can see clearly that the heat rate, millions of BTU per hour, has to be calculated or has to be evaluated at the full load value. That means the full capacity value. So we can calculate it like this: 510 plus 7.2 PG1. So instead of PG1, what we will do, we will be writing the rated capacity or the full load capacity that the unit can take. So that is 600 plus 00142. Then that is PG1 squared, so 600 squared. So that is heat rate calculated at full load capacity multiplied. So this square is actually before the bracket. So that is 600 squared, then the bracket. Then multiplied by the fuel cost. So that is given here 1.1. So it multiplied by 1.1 divided by the rated capacity of unit number 1. So that is 600. So if we do that, then we will get the full load average production cost. Similarly, we can calculate the same thing for unit number 2 as well as for the unit number 3. So as because this is the one sort of cost, that is some sort of average production cost at full load. Okay, when the system is providing the full load, that means the full rated capacity has been used for that specific unit, then what is the average production cost? Okay, this is the explanation of full load average production cost. So once we calculate this, as well as we calculate the full load average production cost for unit number 2 as well as for unit number 3, what we were going to get. Let's see, so what are the values? So the values are listed over here in this table. So for the first unit, we have $9.79 per megawatt hour. For the second unit, it is $9.48 per megawatt hour. And for unit number 3, it is $11.188 per megawatt hour. So we can clearly see that the full load average production costs are not exactly same for all the units. Rather, they're different. And according to their values, we can easily form a priority list. So while we prepare the priority list, of course, our priority should be given for that unit which has the lowest full load average production cost. So following this table, we can clearly say that, well, this is the minimum. So unit number 2 should get the top priority. This is the second one, second highest cost. So this unit number 1 should get the second priority, and the highest costliest unit, the costliest unit should be getting the lowest priority among the units. So this is the dollar per megawatt hour corresponding to full load average production cost for all these 3 units, and these are the corresponding minimum and maximum megawatts which were actually given in the problem statement. So this value, talking about these values. So as unit number 2 is the least cost, so you can take 100 and 400 at first, and then for the remaining one. So you see 100 and 400 at the top associated with unit number 1, unit number 2, then for unit number 1, and then for unit number 3. So this is our priority list. Now, how actually this list is going to help us in solving the problem? So what the priority list actually means is, let's say you have these 3 units. So there could be a possibility, there is a possibility that if we go for all the combinations available among the units, so we can have all the units on. Okay, so if we start from here, skipping the all zero combination. So 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. If I go for the binary combination at first, so we will be getting something like this. Okay, 1, 0, 0, then 1, 0, 1, 1, 1, 0, 1, 1, 1, 2, 3, 4, 5, 6. Yeah. So these are the 7. So I'm skipping the combination where none of the units are on. That means all zero combination has been skipped. So you can see in the priority list scheme, what does it mean? It's basically, first of all, because it is a strict priority ordering, so we cannot turn any of the units which has lower priority without starting the higher priority units. It means if unit 2 is off, we cannot run unit number 1. At the same time, or in other words, we can also say, for example, if unit 1 is off, we cannot run unit number 3. Okay. So what does it mean? If we give the unit numbers here, unit number 1, sorry, 3, 2, 1 in such a manner. So to find out which of the units, which of the combination among the units we can actually consider for solving the problem according to the priority list. So it means because unit number 1 is the top priority, so I can go for unit number 1. I cannot go for, unit number 2 is the top priority, so I cannot go for unit number 1 whenever unit number 2 is off. I cannot start unit number 1 whenever unit number 2 is off, because unit 2 is of higher priority than unit number 1. So because if we look here in the first state, so let's say these are the states 7, 6, 5, 4, 3, 2, 1. So in the state number 1, we can see that unit number 1 has to be turned on without turning on unit number 2. So according to the priority scheme, priority ordering, unit 2 is of higher priority. So this one should not be a feasible state, not a feasible state. So let's see if we write down the feasibility. So this one is not a feasible state. Then we check state number 2. We can see, well, I'm turning unit number 2 while both unit 1 and unit 3 are off. So unit number 2 is the topmost priority. So this is a feasible state. Let's check state number 3. Here both unit 1 and 2 has to be turned on. So yeah, okay, no problem. So I'm turning on unit number 1 as well as unit number 2 while the lowest priority unit is off. So this is okay. State number 4, I have to turn on unit number 3 without turning on the higher priority units. So that is not a feasible state. State number 5, the topmost priority unit is off. So others cannot be turned on. So that is not feasible. Okay, in state number 6, I cannot turn on unit number 3 unless I am turning on both 2 and 1. So here 1 is off, so I cannot turn on unit number 3. So this is not feasible. Here all are turned on. Yeah, that is possible because I'm turning on unit number 2, then unit number 1, and then unit number 3. So that is possible. So you can see among these 7 possible states, I'm only getting 3 states which are feasible. And this is only because I am following a strict priority ordering. So I have to choose either state number 7 or state number 3 or state number 2 when I am playing with the unit shutting, unit turning on, or unit commitment or unit decommitment. Okay. So if that is the case, what is the benefit? The benefit is, of course, we don't have to check all of the possible states. Okay, we don't have to check all the possible states. And of course, in the strict priority ordering, we are actually taking care of the cost optimality. Okay, implicitly, we are taking care of the cost optimality. That means the lowest cost unit has been turned on at first. Then the next lowest cost unit has been turned on, and finally the highest cost unit has been turned on to supply the demand. So implicitly, we are actually taking care of the cost optimality when we are talking about the strict priority ordering. So how we are going to solve the problem? Remember, the problem was, it was asked that how we are going to shut down the units. So if we have a variation in the demand like this, of course the demand will be varying, although a fixed demand was shown here. So you may also consider a variable demand here. Okay, instead of 550, the demand might vary, keeping all the other information same. You can say, well, if the demand varies, then how we are going to shut down the units following the priority ordering. So as we said, if the demand is between 400 and 1000, anything lower than 1000, then what we can do, if the maximum demand is 400, we can only turn on unit number 2. Why? Because our first unit capacity, maximum capacity, it can supply 400. So if anything is beyond 400, then we have to turn on the next unit, because we cannot supply the demand running only unit number 2 then. So if the demand is a maximum of 400 megawatt, then according to the priority list, we have to first go to unit number 2. We cannot go to unit number 1. So that means the state number 2 should be made active. State number 2 should be made active, where only unit number 2 is present. That is valid only up to a demand of 400 megawatt maximum. If the demand goes beyond 400 megawatt, then which state should be made available? Which state should be activated? Now let's look at what are the feasible states. So this is already been done. So next we have to turn on, if the demand increases from 400, then we have to turn on unit number 1 as well as unit number 2. Okay, so you see the next, that is 600 available. So in total we can have a maximum of 1000. So that means both unit 2 and unit 1 has been turned on. So unit 2 as well as unit 1, that means we are talking about state number 3. So the transition will be from state 2 to state 3, because no other intermediate states are feasible. That means if the demand, let's say, is 500, if the demand is 500, that means we could have chosen only unit number 1, and we could have turned off unit number 2. But because we are following a strict priority ordering, we cannot do that. As I said, we cannot turn on a lower priority unit by keeping a higher priority unit off. So although we could say that, well, what is the problem if I choose this one, state number 1, because in state number 1, unit 1 is on, and the maximum capacity is 600 megawatt, which is well above the load demand of 500 megawatt. But because as I said, this is not a feasible state, I explained earlier, so we cannot go for that choice. So the only choice is to turn on both unit 2, the highest priority unit, and the next highest priority unit, unit number 1, to supply any demand between 400 to 1000. So that is the solution. If the demand goes beyond 1000, then the remaining feasible state has to be activated. That means all the units should be taken, and a maximum of 1200 can be supplied using these 3 units. Okay, so this is the example of priority list scheme for solving unit commitment problem. Okay, And the solution is actually shown in the tabular form in the next slide here. So if we choose unit number 2 alone, that's the top priority unit, then you can supply a maximum of 400. And of course, the associated minimum megawatt is there. If the load demand goes beyond 400 and it is up to 1000, then you can choose unit 2 and 1, both of them. And of course, if the demand is more than 1000 and up to 1200, then you have to choose the last unit, which is unit number 3. Of course, in this priority list scheme, we are not taking into account all these constraints, like what is the startup cost, or the costs of starting up the unit is not taken into account. The minimum uptime and downtime and any other constraints are not actually taken into consideration. So this, we can say, a simple, very simple example. Okay.